In this lecture, we will do problem solving on the phenomena of beats. Beats refers to one rise and one fall in sound. And pictorially, if this is the wave function that represents superposition of two sound waves arising from, say, two tuning forks, then this has the structure in the abscissa we have time, and the oscillations are modulated as shown here, and there is a rise followed by a fall, a rise followed by a fall, a rise followed by a fall. So this is a beat, this is a beat, this is another beat. As mentioned in the previous lecture, one application of beats was determination of unknown frequency. In today's lecture, we will do problem solving based upon this application. We shall do a large number of problems, but before that, let us address two important questions. One is how to increase frequency, and the other one is how to decrease frequency. Suppose we are considering a tuning fork and its frequency, natural frequency is 280 Hz. Now we can file it. Filing means rubbing. As a result of which a portion of it is removed. So what happens due to rubbing is, or filing is, that it loses mass. So if the tuning fork loses some mass, its inertia decreases. It becomes more agile. That is, can vibrate faster, meaning that the frequency can rise. So the frequency now increases to, say, 280 Hz, and the process through which we can achieve it, that is, through which we can increase the frequency of a tuning fork, is a filing, that is, rubbing it. On the other hand, this 280 Hz of the tuning fork can be decreased by loading it with wax. So by waxing it or loading with wax. The loading wax on a prong. So we have loaded it with wax, as a result of which frequency can decrease, say it decreases to 274 Hz. Why? Because it gets heavier, so it gains mass. inertia rises, it becomes slower, it becomes less agile, takes more time to vibrate. As a result of which frequency decreases. In fact, fatter means slower, while slimmer means faster. Slimmer means faster, but fatter means slower. On the other hand, if we have a string, a stretched string, say that of a piano, so in that case, we can think of this formula where mu is mass per unit length, T is tension, V is the speed of sound, and L is the length of the stretched string. Now if the string is more tight, means more tension, then frequency will increase. So the opposite will be to make the string slackened. Or loosen it so that the tension will be less. So if T goes down, tension goes down, frequency decreases. So these are the methods which we have discussed. Let me make a gist, and here it is. Frequency of a tuning fork can be increased by filing and decreased by loading it with wax or waxing. Frequency of a string can be increased by making the string more tight, that is increasing the tension, and frequency of the string can be diminished or decreased by making it slackened or making it less tense. We now go over to problem solving directly. Let us note down the problems. A tuning fork, and let us call the tuning fork A. It has frequency 280 Hz, is sounded with another source of frequency, say F, and the source is either a tuning fork, which we call B, or a string, say a piano string, which we call C. Now when A and B or A and C are sounded together, they produce bits, and the number of bits heard is, say, 6 bits per second. Now some processes are done on A, B and C, and they are the following processes are performed. And what are they? Number 1, tuning fork A is filed, that is rubbed. Tuning fork A is waxed in another experiment. In another experiment, the tuning fork B is filed, or if you are doing the experiment with the string, then that string C is pulled tight. In another experiment, B is waxed, or equivalently C is slackened. In fifth experiment, A is filed and B is waxed, or C is slackened. And in the last experiment, A is waxed and B is filed. Filed, or equivalently C is made tight. So under these processes, we have to find F, where F is the unknown frequency, and the observations are: A, 4 beats are heard. 4 beats per second are heard, or if 8 beats per second heard, or 6 beats per second is heard, or no beats are heard. So let me make a gist of the problem. There are 1, 2, 3, 4, 5, 6 multiplied by 1, 2, 3, 4. So 24 problems here, and each can be done very easily in a single step. But let me mention the problem. The experiment is done using 2 tuning forks A and B, or the experiment is done using a tuning fork A with a string that we name C, and it is known that the frequency of A is 280 Hz, and when A and B or A and C are sounded together, number of beats heard is 6. Now we do some processes on A or on B or C, or both on A and B or A and C, and then one hears 4 beats per second or 8 beats per second or 6 beats per second, or fails to hear any beat. Under this situation, we have to determine the unknown frequency of B, or if the experiment is done with C. And the processes which we will perform are either 1 or 2 or 3, 4, 5 or 6. There are 24 problems that we will finish or solve in no time, just by putting the frequencies correctly on the frequency line. And here it is. Frequency increases from left to right, and tuning fork A has frequency 280 Hz, which is, say, here. When sounded with B or C, 6 beats are heard per second, which means the frequency of B or C can be either 280 plus 6, that is 286 on the high frequency side. This is A. Or another possibility is that the frequency of B or C can be 280 minus 6, that is 274 on the low frequency side. In either case, number of beats heard is the difference of frequencies, so it is 6. Or if B or C lies on the low frequency side, this difference is the number of beats heard per second. So the problem has been set up, and let us focus attention to problem 1, which says that A is filed. A being filed or rubbed, it loses mass, inertia decreases, it becomes lighter, it will vibrate faster, and so its frequency increases. So it will be 280 plus something, which let us denote by 280 plus. So this is the 280 line, this is 286 line, and this is 274 line, and 280 plus line is, say, this one. Under this situation, the bits that these two frequencies would produce will be less than 6, so let us denote it by 6 minus, and by these two frequencies will be greater than 6, so let us denote it by 6 plus. Now let us go to problem A. 4 beats per second is heard and 4 is 6 minus, which means the tuning forks involved have frequencies. One is 280 plus that of A, and B or C will have frequency 286. So answer 2, 1A is 286 Hz. This is 4. Let us come to the next problem. 8 beats per second is heard, and 8 is actually 6 plus, it is greater than 6, which means the frequencies involved in producing 8 beats per second will be, one is 280 plus, the other one will be that of B or C, which will be 274. So this is actually 8. So the problem 1B will have answer 274 Hz, the frequency F of B or C. Two problems having solved, we mentioned that in these two problems, 1A and 1B, the frequency of A due to filing increased from 280 to 280 plus, which we took to be here. Now we come to problem 1C. According to which number of beats did not change. So even after filing, even after rubbing, number of beats did not change. It is still 6. But rubbing will definitely increase its frequency. It is clear that difference 6 cannot be achieved between 280 plus and 274. It is always greater than 6. So the possibility 274 is ruled out. Due to rubbing, suppose the frequency of the tuning fork A increases from 280 to, say, 292. So this is actually 280 plus. And then the beats per second that will be heard will be the difference between 292 and 286, which is 6. This means number of beats heard will be 6 if the frequency of B and C is 286. And we come to the last problem. No beats are heard. Due to filing or rubbing of A, suppose its frequency increases from 280 to 286. So now we have two tuning forks, both of frequency 286. So now 286 is actually 280 plus. So both A, this is of A, and B or C have frequencies 286. So 286 minus 286 is 0, and therefore number of beats heard will be 0. No beats will be heard. So the answer is again 286 Hz, the frequency of B and C, which makes it possible. Let us now move to problem 2, which states that the tuning fork A is waxed, that is loaded with wax. So its inertia increases, it refuses to move fast, it moves slowly, it vibrates slowly, and therefore its frequency falls. And let it fall to, say, 280 minus, that is obviously less than 280 Hertz. So somewhere here, so this is 280 minus in problem 2. Now the possible number of bits are, which is less than 6 if the frequency of B or C is 274 Hertz. So let us call it 6 minus, or it is greater than 6. So let us call it 6 plus. We now come to problem 2a, which says that 4 beats per second is heard, and 4 is 6 minus, it is less than 6. So the frequency of B or C in this situation would be 274 Hertz. So the answer is 274 Hertz. This is 4. In problem 2b, number of beats per second is 8, which is greater than 6, that is 6 plus. So now the vibrating sources are having frequency 280 minus and 286. So this is 8. So the answer is 286 Hertz. We next come to problem C, which says that number of beats heard is 6 in spite of waxing of A. In problem 2a or 2b, due to waxing of A, the frequency decreased from 280 Hertz to some lower value denoted by 280 minus, which we took here. Now in problem C, we note that this value, which is less than 280 and 286, cannot differ by 6. Rather, it differs by more than 6, that is 6 plus. So 286 Hertz is ruled out. Now, due to waxing of A, suppose the frequency of the tuning fork A becomes less and less to say 268 Hertz, which is 280 minus, that is less than 280. So now number of beats heard will be the difference between 268 and 274, which is 6. So the answer to problem C is 274 Hertz. This is the answer to problem 2C. Next problem is that no beats are heard. Due to waxing of A, suppose the frequency diminishes from 280 to say 274. Then the two vibrating sources, namely A vibrates with 274 and B or C also vibrates with 274 Hertz, and therefore 274 minus 274 is 0, which means no beats are produced. So the answer is, in case of D, it is 274 Hertz. We shall now move on to the next set of problems, which is set 3, in which B is rubbed or C pulled tight, as a result of which the frequency of B or C increases from 286 to say here, which is 286 plus, if B or C has higher frequency, or from 274 to somewhere here, which let us denote by 274 plus. So frequency increases. As indicated, number of beats would thus become greater than 6, which we call 6 plus, if B or C has frequency higher than 280, while number of beats is reduced from 6 to a lower value, which let us call 6 minus, if B or C has frequency lesser than 280. Let us now address problem A, and here it is. Beats heard is 4 per second. So in problem 3A, 4 is less than 6, so this is 4. So the answer is that B or C has frequency 274. Only then 4 beats can be heard. Let us come to the next problem, 3B, according to which 8 beats are heard, which is greater than 6, so it is 6 plus. So now this is possible only if the frequency of B or C is on the high frequency side, that is, the answer will be 286 Hz for F. Next is problem C, which says that in spite of rubbing B or making C tighter, beats heard are 6 in number as before. This means that the difference of frequency of B or C with 280 frequency of A should be 6. Now the difference cannot be 6 for 286 plus and 280. It is actually greater than 6. So 286 is ruled out. After filing B or pulling tight C, the frequency 274 can increase to, say, 286, and then number of beats heard between 286 and 280 is 6. So the answer to C is 274. It was 274 that was shifted to 286. The last problem says that no beats are heard. And this means the vibrating sources have same frequency. One source is A, the other source should also vibrate with 280. Now 286 cannot decrease, it can only increase because we are rubbing B or making the wire of C tighter. So 286 is again ruled out, and due to the process 274 frequency suffers an increase and it becomes 280 Hz. So now the vibrating sources, that is A and B or C, are vibrating with frequency 280, and therefore no beats are heard. So the answer for no beat case, that is case D, will be 274 Hz, because we can get to this point not from 286 but from 274. We next come to problem 4, according to which B is waxed, that is loaded with wax, or the string of C is slackened so that the frequency of B or C decreases from 286 to, say here, which is 286 minus in the high frequency side, and from 274 to say 274 minus on the low frequency side. So number of beats produced might be lesser than 6. That is 6 minus if B or C is on the high frequency side, and it is greater than 6, that is, say 6 plus if B or C is on the lower frequency side. So this is problem 4. We come to problem 4A, according to which 4 beats are heard, and 4 is less than 6 it can be 6 minus. So the answer is 286. In problem 4b, number of bits heard is 8, that is greater than 6, so it is 6 plus. So the answer is 274 Hz, which is possessed by B or C before it is waxed. Next problem is C4C, in which 6 bits per second is heard. Now, the difference between 280 and 274 minus cannot be 6. It is more than 6, that is 6 plus. So 274 is ruled out. Due to waxing of B or making string of C loose, 286 can become less and less until it is 274, when the difference between 280 and 274 is 6. So answer is 286. And problem D is that no bits are heard. The sounding sources, therefore, should have the same frequency. Now 274 can only decrease, and so it cannot reach 280. So 274 is ruled out. But on waxing B or on making string of C loose, the frequency 286 can be diminished to 280. And then we have a situation where both A and B or C are vibrating with frequency 280 to produce no bits. So the answer is 286 Hz. In problem 5, tuning fork A is filed, so frequency of A increases from 280 to 280 plus, and B is waxed or C is slackened, which means their frequency is decreased from 286 to 286 minus if they had frequency in the high frequency side, or from 274 to 274 minus in the low frequency side. So A suffers frequency increase and B or C suffers frequency decrease. Number of bits heard will therefore be less than 6. Let us call it 6 minus on the high frequency side, and greater than 6, that is say 6 plus if B or C has frequency in the low frequency side. We now come to problem A, according to which 4 bits are heard and 4 matches with 6 minus, it is less than 6. So this is 4. So the answer is 286. In B, it is given that 8 bits per second is heard, and 8 is 6 plus, so this can be 8. So the answer is 274. In problem C, 6 bits per second is heard. Now the difference of frequencies 280 plus and 274 minus can never be 6. It is always greater than 6. So 274 is ruled out. Now the difference between 280 plus and 286 minus can be 6 in many ways, one of which is the decrease of 286 occurs by this amount, that is 286 becomes 280, and the increase of 280 becomes of this amount, that is 280 goes to 286. So now number of bits heard will be the difference between 286 and 280, that is 6. So the answer is 286. And the last one is that when no bits are heard, that is when the frequencies of the two sources matches. Now since 280 increases and 274 decreases, there is no possibility of match between these two frequencies, so 274 is ruled out. Matching of these two frequencies can occur in various ways. One such might be that 280 increases and comes here, while 286 decreases and comes here, so that the two sources A and B or C are vibrating at this frequency, the difference of which is 0, leading to 0 bits. So the answer is 286. We now move on to the last problem 6, in which it is said that A is waxed, which means its frequency will decrease to say 280 minus, and B is filed or C string is made tighter, which means their frequencies are increased. So the frequency 286 increases to somewhere here, and it is 286 plus if it is on the high frequency side of A, while if it is on the low frequency side, the increase is so this is 274 plus. The bits heard will be greater than 6 if it is on the high frequency side, call it 6 plus, but less than 6 if it is in the low frequency side, and call it 6 minus. We now come to problem A, according to which 4 bits are heard and 4 is less than 6, it is 6 minus. So the answer is 274. Problem B says 8 bits are heard and 8 is greater than 6, it is 6 plus. This is 8. So answer to B is 286. We now come to problem C, according to which 6 bits are heard. So the difference of frequencies of the two sounding sources should be 6. The difference between 286 plus and 280 minus can never be 6. It is 6 plus. So 286 is ruled out. The difference between 274 plus and 280 minus can be made 6 in various ways, and one of which is that 274 after increase becomes 280 and 280 after decrease becomes 274. So the difference of frequencies is 6 bits. So 6 bits will be heard. So the answer is 274. And in problem 6D, no beats are heard. This occurs when the difference of frequencies between the two sounding sources is 0. Now we cannot make the frequencies 286 plus and 280 minus to match, and therefore 286 is ruled out. But the frequencies of 274 plus and 280 minus can be made to coincide in multiple ways, and one such way is 274 increases and 280 decreases, and now the sounding sources A and B or C are vibrating at this frequency so that their difference is 0. So the answer is 274 Hz. We have done 24 problems on beats in such a small period of time, and here are some more similar type of problems. A, B, C, D, E, F, G.